What if I told you that everything we can see, the stars, the galaxies, even our own hands, makes up less than 20% of the universe's total mass? The rest is an invisible, enigmatic force known as dark matter, a cosmic ghost that shapes the very fabric of space yet refuses to reveal itself. It's the universe's greatest unsolved puzzle, and at the heart of this mystery lie dark matter halos, vast, invisible structures that wrap around galaxies like cosmic spiderwebs, holding them together with gravity we can't even see. These halos are the hidden architects of the cosmos, sculpting everything from the tiniest dwarf galaxy to the largest superclusters. But how and why do they remain so stubbornly elusive? Picture this: you're standing under a starry sky, gazing up at the Milky Way. What you can't see is the colossal dark matter halo enveloping our galaxy, a shadowy giant 10 times more massive than all its stars combined. Without it, the Milky Way would fly apart, its stars scattering into the void. Yet, despite its overwhelming presence, dark matter leaves no trace, no light, no heat, no direct signal for our telescopes to catch. It's like trying to study a ghost by the breeze it leaves behind. Scientists have spent decades chasing these phantoms, using everything from supercomputers to particle colliders, and still, the answers slip through our fingers like mist. That's where this journey begins. Over the next 25 cosmic mysteries, we'll dive deep into the secrets of dark matter halos, how they form, how they warp the universe around them, and why they might hold the key to understanding everything from the birth of galaxies to the fate of the cosmos itself. We'll unravel bizarre theories, from hidden dimensions to undiscovered particles, and explore the cutting-edge experiments that could finally crack this enigma wide open. So buckle up. Whether you're a seasoned space enthusiast or just curious about the universe's hidden layers, you're about to embark on an adventure that will change how you see the night sky and the invisible forces ruling it. The cosmos has been keeping secrets. It's time we uncover them. The first mystery of dark matter halos is also the most fundamental. These invisible giants dominate galaxies in every way, yet reveal nothing of themselves. Picture a spinning carousel. The horses and decorations are what you see, the bright stars and glowing gas of a galaxy. But the entire ride is bolted to a massive, hidden structure beneath the floor, unseen but holding everything together. That's a dark matter halo. While the Milky Way's visible stars span about 100,000 light-years, its halo stretches 10 times farther. A vast, ghostly sphere with no edges, no glow, or just sheer, silent gravity. How do we know it's there? The clues are in the stars themselves. Galaxies rotate so fast that their outer regions should fling into space like sparks from a spinning firework. But they don't. Something invisible, something with colossal mass, must grip them in place. That's the halo's gravitational hand at work, bending space like an unseen anchor. Astronomers even watch distant galaxies warp and split light around them, a phenomenon called gravitational lensing, revealing halos as enormous cosmic footprints pressed into the fabric of reality. The strangest part, these halos aren't smooth. Supercomputer simulations show they're lumpy, filled with dense knots and wispy tendrils, like unseen mountain ranges wrapped around galaxies. Some theories suggest they might even contain ancient black holes or exotic particles from the universe's birth, relics hiding in plain sight. Yet every experiment to catch a direct glimpse, underground detectors, space telescopes, even the Large Hadron Collider, has come up empty. It's as if the cosmos built an entire hidden skeleton and left us only shadows to study. But here's the twist: dark matter halos might not be completely dark. Recent observations hint at faint, mysterious gamma-ray glows around galaxies. Could these be the halo's fingerprints, particles annihilating in the void? Or perhaps we're seeing the halo's gravitational wake, stirring up cosmic gas like an invisible ship cutting through water. Whatever the answer, one thing's certain: These unseen giants hold galaxies hostage to their will, and until we solve their riddle, we're missing half the story of the universe. If dark matter halos hold galaxies together like invisible scaffolds, then where are all the smaller galaxies they should be hosting? This is the second great mystery, why our cosmic neighborhood seems emptier than theory predicts. Imagine dark matter as a vast, intricate spiderweb. Each intersection where threads meet should cradle tiny clumps of gas and stars, forming dwarf galaxies that orbit larger ones like fireflies around a lantern. Supercomputer models show our Milky Way's halo ought to harbor hundreds of these satellite galaxies, yet we've only found about 60, so where did the rest go? Scientists call this the missing satellite problem, and it's been haunting astronomers for decades. The simulations aren't wrong, they're based on solid physics, tracing how dark matter's gravity would sculpt the universe over billions of years. But reality seems to have ignored the blueprint. One possibility: many of these dwarf galaxies formed, but their stars were snuffed out before they could shine. Dark matter halos may have been too efficient, squeezing gas so tightly in some satellites that it collapsed early into supermassive stars, exploding violently and stripping away star-forming fuel. Others might have been ripped apart by our galaxy's tides, leaving behind only ghostly streams of stars like cosmic breadcrumbs. Then there's the too big to fail puzzle. Some of the Milky Way's surviving satellites, like Draco and Ursa Minor, are bizarrely massive, packed with dark matter yet strangely dim. If dark matter halos are as lumpy as simulations suggest, these dwarfs should have enough gravity to birth far more stars. Instead, they're cosmic underachievers, flickering faintly in the void. Could some unknown force, a dark matter-particle interaction, or even early radiation from the universe's first stars have choked their growth? The hunt for answers is pushing telescopes to their limits. Projects like the Vera Rubin Observatory are scanning the skies for ultra-faint dwarfs, galaxies so dim they're practically invisible, hiding in plain sight. Others probe the chemical fingerprints of stars in these satellites, searching for traces of explosive deaths that might explain their stunted growth. Meanwhile, alternative theories are gaining traction. Perhaps dark matter isn't entirely cold but slightly warm, with particles just energetic enough to smooth out halos and reduce satellite numbers. Whatever the solution, the missing satellites remind us that dark matter halos aren't just static structures, they're dynamic, even destructive forces. They don't just build galaxies, they might break them too, and until we find those vanished dwarfs or understand why they never shone, our map of the cosmos will remain frustratingly incomplete. The universe's hidden architects are still teasing us, leaving empty spaces where galaxies should be. When we peer into the heart of a dark matter halo, we find a cosmic tug of war between theory and reality, one that's been raging for over 2 decades. At the center of this battle lies the cusp core controversy, a puzzle that challenges everything we thought we knew about how dark matter behaves. Supercomputer simulations consistently paint halos with steep, dense cusps at their centers, regions where dark matter particles should pile up like snowdrifts under gravity's relentless pull. But when astronomers study real dwarf galaxies, the stars inside them move as if the halo's core is strangely flat, almost like a gently rolling hill rather than a jagged peak. This mismatch isn't just academic, it cuts to the very nature of dark matter itself. If halos truly have dense cusps, then the particles must be cold, slow-moving, and clumping easily in the early universe. But if cores are real, something must have smoothed them out, either because dark matter is subtly different than we thought, or because forces we don't yet understand reshaped them. One tantalizing clue comes from ultra-faint dwarf galaxies like Segway 1, where stars drift so lazily that their motions suggest an almost hollowed-out center. It's as if an invisible hand reached in and scooped away the densest dark matter, leaving behind a ghostly bowl. Could ordinary physics explain this? Some theorists point to supernova, the explosive deaths of massive stars whose shockwaves might have pushed dark matter outward, flattening the core over billions of years. Others argue that if dark matter particles can interact weakly with each other, not just through gravity, collisions in the crowded halo center might have softened the cusp into a core. Then there's the radical idea that dark matter isn't a particle at all, but a mysterious field that naturally resists piling up too densely. The stakes couldn't be higher. If cores win, we might need to rewrite the rules for how structure forms in the universe. Already, alternative theories like self-interacting dark matter or fuzzy dark matter, where particles have bizarre quantum properties, are gaining traction. Yet cusps still have defenders who argue that observational uncertainties like the exact positions of stars in dwarfs could be skewing the data. New telescopes might finally settle the debate. The James Webb Space Telescope is probing faint stellar motions in distant dwarfs, while radio astronomers search for dark matter's faint whispers in hydrogen gas clouds. Whatever the answer, the cusp core controversy reminds us that dark matter halos aren't just static backdrops, they're dynamic, evolving enigmas, and their centers might hide the keys to unlocking the universe's deepest secrets. If dark matter halos are the universe's invisible scaffolding, then why do some of the largest cosmic structures seem to be missing their galaxies? This is the too big to fail problem, a paradox that's left astrophysicists scratching their heads. Imagine building a colossal stadium designed to hold thousands of roaring fans, only to find it eerily empty on game day. That's what simulations of dark matter halos predict. Vast, gravitationally dominant structures so massive they should cradle thriving, luminous galaxies. Yet when we look, many of these halos host nothing more than a few dim, scattered stars. The puzzle emerged when supercomputer models revealed halos with enough gravitational pull to form galaxies as bright as the Milky Way's most famous satellites, like the Large Magellanic Cloud. Yet in reality, we find halos of similar size containing only faint dwarf galaxies, their stellar populations a fraction of what they should be. It's as if the universe forgot to flip the switch on star formation in these places. One leading explanation, cosmic feedback, the idea that early bursts of star birth and death might have blasted away the gas needed to form new stars. Picture a young dwarf galaxy, its first generation of stars igniting in a frenzy. These massive stars live fast and die violently, exploding as supernova that heat surrounding gas to millions of degrees, pushing it out of the halo's grasp. Without fresh fuel, later generations of stars simply couldn't form, leaving the galaxy stunted. But feedback isn't the only suspect. Some theorists argue that dark matter itself might be to blame. If dark matter particles interact even weakly, bumping into each other like billiard balls, these collisions could redistribute energy within the halo, smoothing out its core and stifling star formation. Others propose that ultraviolet radiation from the universe's first galaxies, blazing forth during the cosmic dawn, might have sterilized smaller halos by stripping electrons from their gas atoms, rendering it too hot to collapse into stars. The search for answers is driving astronomers to the edges of detection. Telescopes like the James Webb are peering into ultra-faint dwarfs, hunting for chemical fingerprints of those early supernovae. Meanwhile, revised simulations now incorporate more nuanced physics, like the turbulent churning of interstellar gas, to see if they can reproduce these failed giant halos. One thing's clear, the too big to fail problem isn't just about missing galaxies, it's a cosmic clue, hinting that dark matter halos and the galaxies they host don't play by the simple rules we once assumed. And until we solve it, our understanding of galaxy formation remains frustratingly incomplete, like a puzzle with half the pieces still hidden in the dark. Sometimes the universe hands us the perfect cosmic experiment, and the bullet cluster is one of those rare gifts. Picture two galaxy clusters, each with hundreds of galaxies, hurtling toward each other at millions of miles per hour. When they collided, the result was a celestial fireworks show so violent it ripped the fabric of space itself. But the real shock wasn't the collision, it was what it revealed about dark matter. Here's how it works. Galaxy clusters aren't just stars and galaxies, they're also filled with superheated gas that glows in X-rays. When these two clusters smashed together, their gas clouds slammed into each other like tidal waves, creating a shockwave visible to telescopes. But something bizarre happened to the galaxies. They sailed right past each other, barely disturbed, as if they were phantoms. And that's not all. By mapping the cluster's gravity using gravitational lensing, the way it bends light from distant objects, astronomers discovered most of the mass wasn't where the gas or galaxies were. Instead, it lurked in two distinct blobs trailing behind like invisible shadows. This was the smoking gun for dark matter. The gas, slowed by the collision, lagged behind. The galaxies, mostly empty space, barely interacted, but the dark matter, it kept going, unfazed, as if the collision never happened. Why? Because dark matter doesn't interact with light, gas, or even itself the way normal matter does. It's a ghost passing through everything without a whisper. The bullet cluster proved beyond doubt that dark matter isn't just a theoretical concept. It's real, it's out there, and it's shaping the cosmos in ways we're only beginning to grasp. But the mystery deepens. If dark matter is so dominant, why didn't it slow down? Some theories suggest its particles might interact weakly, like distant ships passing in the night. Others wonder if dark matter halos have intricate substructures, invisible threads that weave through galaxies unnoticed. The bullet cluster didn't just confirm dark matter's existence, it handed us a new set of riddles, proving that even our best evidence comes with unanswered questions. What's next? Astronomers are now hunting for more cosmic collisions, hoping to catch dark matter in the act again. Each new cluster smash-up could reveal whether dark matter behaves the same everywhere, or if it has tricks we haven't seen yet. One thing's certain, the bullet cluster showed us the invisible hand holding the universe together, and it's only the beginning of the story. Even our home galaxy, the Milky Way, hides a dark matter secret. Its halo isn't the perfect, symmetrical sphere we once imagined. Instead, new research suggests it might be warped, lopsided, even torn, like a cosmic cloak caught in a storm. This isn't just a curiosity. It could explain why the Milky Way's satellite galaxies are arranged so strangely, clumped together in an uneven plane that defies conventional models. Take a closer look at our galactic neighborhood. Most of the Milky Way's known satellites, dwarfs like Draco, Sculptor, and the Large Magellanic Cloud, aren't scattered randomly around us. Instead, they're clustered along a rough plane, almost as if they're orbiting along an invisible highway. Conventional dark matter theory predicts these satellites should be distributed more evenly, like bees buzzing around a hive. But nature, as always, has other plans. One explanation: the Milky Way's dark matter halo might be off-center, its gravity warped by a long-ago collision with another galaxy. Picture a rock dropped into a pond. The ripples don't just fade symmetrically, they swirl and distort. If a smaller galaxy plowed through the Milky Way's halo billions of years ago, it could have dragged dark matter with it, creating a gravitational imbalance that still lingers today. Alternatively, the halo might not be perfectly cold. If dark matter particles have even a tiny amount of intrinsic motion, they could create a lopsided dynamic structure over time, like a slowly tilting top. Then there's the galactic bar, the Milky Way's central bulge of stars that rotates like a rolling pin. Some simulations suggest this bar might churn the inner halo, twisting its shape and sending ripples through the outer regions. If dark matter responds to these gravitational tides, it could explain why some satellite galaxies seem to pile up along certain orbits, like leaves caught in a whirlpool. The implications are profound. If our halo is irregular, it challenges the idea that dark matter halos are always smooth and symmetrical, a cornerstone of many cosmological models. It could also mean that the Milky Way's history is far more violent than we thought, shaped by ancient collisions that left scars in the invisible fabric of its halo. Upcoming missions like the European Space Agency's Gaia spacecraft are mapping stellar motions with unprecedented precision, hunting for subtle gravitational tugs that might reveal the halo's true shape. For now, the Milky Way's warped halo remains a tantalizing hint, a shadowy reminder that even in our own cosmic backyard, dark matter refuses to follow the rules. And if our galaxy's halo is this unpredictable, what other surprises might lurk in the darkness beyond? What if dark matter isn't just a formless cloud surrounding galaxies, but something far more structured, like an invisible disk hiding in plain sight? This is the provocative idea behind the dark disk hypothesis, a theory that could rewrite our understanding of how spiral galaxies like the Milky Way actually work. Most models assume dark matter halos are roughly spherical, enveloping galaxies in a shapeless gravitational embrace. But what if some of that dark matter settled into a thin, dense plane, spinning alongside the stars and gas we can see? The clues lie in the stars themselves. Astronomers have noticed something odd about the motions of stars near the Milky Way's midplane. They don't quite match predictions from traditional spherical halo models. Some stars seem to wobble more than expected, as if tugged by an unseen force. Others move with a strange synchrony, like dancers following a rhythm we can't hear. A dark disk could explain these quirks, adding an extra layer of gravitational influence that's been overlooked. Think of it like this: if the Milky Way were a vinyl record, the stars and gas would be the grooves you can see, while the dark disk would be the hidden weight stabilizing the spin beneath the surface. But not everyone's convinced. Critics argue that a dark disk would require dark matter to behave in ways we've never observed, slowing down and clumping into a flattened structure, as if it were interacting with itself or with ordinary matter in unexpected ways. After all, dark matter's defining feature is its reluctance to collide or emit light, so how could it settle into such an orderly arrangement? Some simulations suggest cosmic turbulence, giant waves of gas stirred by spiral arms or passing satellite galaxies might have herded dark matter into a disk over billions of years. Others speculate that a long-ago merger with a smaller galaxy could have funneled dark matter into the plane, like sprinkling sand onto a spinning plate. The debate hinges on two competing visions of dark matter, one where it's entirely passive, drifting like fog through the cosmos, and another where it's subtly dynamic, shaped by forces we're only beginning to grasp. If the dark disk is real, it could solve multiple mysteries at once, not just stellar motions, but also the strange distribution of some satellite galaxies, and even the peculiar trajectories of certain asteroids in our own solar system. Right now, the evidence is tantalizing but thin. Telescopes are scouring the Milky Way for more stellar oddities, while physicists revisit particle models to see if any dark matter candidates could plausibly form such a structure. Whether the dark disk exists or not, the very idea challenges us to rethink the invisible scaffolding of the universe, not as a static backdrop, but as something alive with hidden complexity, shaping galaxies in ways we're only starting to imagine. Perhaps the most intriguing possibility: if dark matter can take on structured forms like disks, then its role in galactic evolution might be far more intricate than we ever suspected. Maybe, just maybe, the cosmos isn't merely built on dark matter. It's in conversation with it. Imagine a galaxy so faint it's almost invisible, a cosmic ghost sprawling across space with stars scattered so thinly you could fly through it for millennia without spotting a single one. Now imagine that this wisp of a galaxy, despite its emptiness, weighs as much as the Milky Way. This isn't science fiction. It's the enigma of ultra-diffuse galaxies like Dragonfly 44, celestial paradoxes that defy everything we thought we knew about how galaxies form. Here, in these shadowy realms, dark matter doesn't just dominate, it reigns supreme, making up 99.99% of their mass. How can something so vast, so heavy, be so eerily devoid of stars? The answer lies in the dark matter halo itself. Most galaxies, like our Milky Way, are anchored by halos that strike a balance, enough gravity to pull in gas and ignite stars, but not so much that it chokes their growth. Ultra-diffuse galaxies, though, seem to have halos that missed the memo. Their dark matter is spread out like an overstretched net, creating a gravitational field so weak that star formation sputters instead of sparks. Picture trying to light a campfire in a hurricane. The gas needed to birth stars gets stretched too thin, leaving the galaxy trapped in a state of perpetual dimness. But Dragonfly 44 isn't just an outlier, it's a challenge to the rules. Standard models predict that a halo this massive should have attracted enough gas to blaze with stars. Instead, it's a cosmic desert, its few stars adrift in an ocean of darkness. One theory suggests these galaxies might be failed giants, halos that formed too late in the universe's history, after most of the gas had already cooled and settled into brighter galaxies. Another idea, they could be the survivors of catastrophic collisions, their gas stripped away by violent encounters with larger galaxies, leaving behind only their dark matter skeletons. Even stranger, some ultra-diffuse galaxies appear to have almost no dark matter at all, like NGC 1052, a wispy contradiction that somehow exists without the invisible anchor every other galaxy relies on. This flip side of the mystery hints that dark matter halos might be more versatile or more elusive than we ever imagined. Could these faint galaxies be teaching us that dark matter isn't just a monolithic force, but something that interacts with the universe in ways we're only beginning to glimpse? The hunt for answers is pushing telescopes to their limits. Observatories like the Keck and Hubble are peering into these ghosts, measuring the faint tug of their gravity on distant starlight to map their hidden halos. Meanwhile, simulations are scrambling to recreate them, tweaking variables like gas density and cosmic timelines to see if any combination spawns these ethereal giants. Every discovery chips away at our assumptions, revealing a cosmos where dark matter doesn't just lurk in the shadows. It sculpts them, crafting galaxies that glow faintly in the void, whispering secrets we're only starting to hear. If dark matter halos are the cosmic glue holding galaxies together, why do some of the universe's oldest galaxies seem to be missing them entirely? This is the startling puzzle known as the dark matter drought, where observations of early galaxies reveal a bizarre mismatch. These ancient stellar cities rotate and behave as if they're barely anchored by dark matter at all. It's like finding a skyscraper standing tall with no foundation, defying every law of physics we know. The evidence comes from galaxies like the Wolf Disk, a spinning marvel dating back just 1.5 billion years after the Big Bang. Normally, a disk galaxy this mature should be enshrouded in a massive dark matter halo to keep its structure intact. Yet when astronomers measured its rotation, the stars moved as if the halo's gravitational hand was barely there. Similar oddities pop up in other primordial galaxies, where gas clouds swirl too slowly for the amount of visible matter present, suggesting dark matter hasn't fully settled into its expected role. So where was the dark matter? One possibility is that it arrived late. In the early universe, dark matter may have been more evenly spread out, like flour not yet sifted into clumps. Ordinary matter, drawn together by electromagnetic forces, could have collapsed into galaxies first, while dark matter, only interacting via gravity, lagged behind, taking billions of years to condense into the halos we see today. Imagine building a house before the cement mixer arrives. The structure exists, but its full strength isn't apparent yet. But there's a catch. If dark matter was truly absent early on, how did these galaxies form at all? Simulations show that without halos to seed their growth, early gas clouds shouldn't have collapsed into galaxies so efficiently. Some theorists propose a radical alternative. Perhaps dark matter was there, but invisible even to its own gravity. If dark matter particles were ultra-light with bizarre quantum properties, they might have resisted clustering until the universe cooled enough for their wave-like nature to settle. Think of it like trying to gather smoke with your hands. Early on, it slips through your fingers, but given time, it thickens into something you can grasp. Another clue lies in the cosmic dawn's harsh environment. Intense radiation from the first stars and quasars might have heated dark matter, keeping it too hot to collapse into halos right away. Or perhaps primordial black holes lurking unseen disrupted early halo formation by swallowing dark matter before it could clump. The James Webb Space Telescope is now peering into this epoch, hunting for galaxies that could tip the scales toward one theory or another. The implications are staggering. If dark matter halos were late bloomers, it could rewrite our understanding of galaxy formation, suggesting that the invisible scaffolding of the cosmos didn't just guide structure but evolved alongside it. Every new observation of these ancient galaxies is like uncovering a page from the universe's diary, revealing a time when the rules we take for granted hadn't yet been written. And until we solve the mystery of the dark matter drought, we're left wondering, did the cosmos build its galaxies first and only later weave the dark matter web that holds them together? Scattered across the Milky Way's halo like fragments of a cosmic crime scene, lie ghostly rivers of stars stretched, torn, and drifting in wildly unexpected patterns. These are tidal streams, the remnants of ancient dwarf galaxies and star clusters shredded by our galaxy's gravity. But here's the twist: some of these streams don't just bend, they kink, warp, and split in ways that defy explanation. Something invisible is tugging at them, something with enough gravity to twist stellar rivers but too faint to see. The prime suspect, dark matter subhalos, invisible clumps lurking within our galaxy's larger halo, leaving their fingerprints on everything they touch. Picture a stream of stars pulled from a dwarf galaxy, stretching like taffy as it orbits the Milky Way. In a perfect, smooth halo, this stream should form a graceful arc. But reality is messier. Some streams, like the one torn from the Sagittarius dwarf galaxy, show jagged gaps and sharp turns, as if something massive punched through them. Other streams, like GD1, appear snipped cleanly in half, their stars scattered like beads from a broken necklace. These aberrations aren't random. They're cosmic breadcrumbs pointing to close encounters with dark matter subhalos. The math is compelling. Simulations show that a single subhalo, just 1,000th the Milky Way's mass, could warp a star stream by simply passing nearby. No collision, no flash, just gravity's silent tug, but proving its dark matter isn't easy. Could these disruptions come from visible objects like rogue black holes or globular clusters? Possibly, yet when astronomers account for every known object, the anomalies remain. That's where projects like the Vera Rubin Observatory come in, scanning the sky for fainter, more delicate streams, mapping their kinks with precision. Each distorted stream is a potential roadmap to the unseen. The stakes are high. If these phantom perturbations confirm subhalos, they'll reveal dark matter's lumpy, hierarchical nature, halos within halos like nesting dolls. But if the distortions don't match predictions, we might need to rethink dark matter's properties entirely. Perhaps it's warmer or more interactive than our models assume. Either way, these ghostly streams are more than stellar debris. They're messages from the dark, written in gravity's invisible ink. And as we decode them, we're not just mapping the Milky Way's past, we're uncovering the hidden architecture of the universe itself. Galaxies don't drift through the cosmos alone, they gather in massive clusters, cities of stars bound by something far stronger than gravity's usual pull. These colossal structures, some containing thousands of galaxies, shouldn't hold together based on the visible matter alone. The math simply doesn't add up. That's where dark matter steps in, acting as the cosmic glue that keeps these clusters from flying apart. But here's the twist: dark matter doesn't just bind these clusters, it shapes their very destiny, battling against an even more mysterious force, dark energy. Think of a galaxy cluster like a bustling metropolis. The skyscrapers, the galaxies themselves, are what you see, gleaming with stars and gas, but the true foundation lies beneath the streets, an unseen framework of dark matter woven into a vast web that spans millions of light years. Without it, the cluster's gravity would be too weak to resist the galaxy's motion, sending them careening into the void. That's why dark matter is the ultimate cosmic architect. Its gravity anchors everything from the smallest dwarf galaxy to the largest superclusters. Yet dark matter's role isn't just about brute force, it also dictates how clusters evolve. When galaxies collide within a cluster, their stars rarely crash into one another. There's too much empty space between them. But their dark matter halos, they merge seamlessly like two shadows blending into one. This creates an even more massive gravitational well, pulling in more galaxies over time. It's a snowball effect, with dark matter acting as the hidden hand guiding the cluster's growth. But there's a catch. Dark matter may dominate the cluster's mass, but it's not the only player. Hot gas, superheated to millions of degrees, fills the spaces between galaxies, glowing faintly in X-rays. This gas outweighs all the stars in the cluster combined, yet it's still just a fraction of the dark matter's grip. And then there's dark energy, the universe's mysterious expansion force, pushing clusters apart over cosmic time. In this tug of war, dark matter is the counterbalance, the cosmic mortar keeping structures intact against the relentless pull of an expanding universe. The evidence is etched across the cosmos. Take the Coma cluster, a behemoth containing over 1,000 galaxies. Its galaxies move so fast that, without dark matter's extra gravity, they should have escaped long ago. Even more telling, gravitational lensing, the way clusters warp the light of distant galaxies behind them, reveals dark matter's true power. The lensing is often strongest where there's the least visible matter, proving that dark matter's grip extends far beyond what we can see. So what happens when dark matter's glue meets dark energy's push? It's the ultimate cosmic showdown. On the largest scales, dark energy wins, accelerating the universe's expansion. But within clusters, dark matter holds the line, creating stable islands in an ever-stretching sea. This delicate balance shapes the fate of everything, from the tiniest galaxy to the grandest structures in the universe. And until we understand how these invisible forces truly interact, we're left with a tantalizing truth. The cosmos is held together by a glue we can't see, fighting a force we don't yet understand. If dark matter truly is the invisible scaffolding of the universe, why do some cosmic structures behave as if these ghostly particles are whispering to each other? This is the puzzle of self-interacting dark matter, a theory that challenges the long-held assumption that dark matter particles pass through each other like ships in the night. Observations of colliding galaxy clusters, where halos seem to brush against one another with unexpected resistance, suggest there might be more to dark matter's story than we've imagined. Take the famous Bullet cluster, where two galaxy clusters collided in a cosmic train wreck. While the galaxies and dark matter kept moving, the hot gas between them, visible in X-rays, slammed together and lagged behind. But here's where it gets strange. In some collisions, like the Able 520 cluster, the dark matter appears to have stalled too, as if it encountered an unseen drag. It's the equivalent of watching two crowds walk through each other in a fog, only to realize some invisible force made them slow down. Could this mean dark matter particles occasionally bump into each other, exchanging momentum like billiard balls? The idea isn't as far-fetched as it sounds. Most simulations treat dark matter as collisionless, meaning particles ignore one another entirely. But if dark matter has even a slight tendency to interact, scattering off itself like a gentle breeze nudging leaves, it could explain these cosmic anomalies. Some theorists propose dark matter might have its own version of a weak force, a shadowy counterpart to the electromagnetic interactions that govern normal matter. Others speculate these particles could emit a hypothetical dark photon, a carrier of force we've yet to detect. Yet not all collisions agree. The musket ball cluster, another galactic smash-up, shows dark matter behaving perfectly as expected, gliding through itself without a hint of friction. This inconsistency has astronomers divided. Could the discrepancies stem from differences in collision speed or halo density? Or do they hint at multiple types of dark matter, some interactive and some aloof? The answer might lie in the wreckage of dwarf galaxies. If dark matter interacts with itself, dense subhalos in these small galaxies should gradually erode, their particles scattering outward like sandcastles in a tide. Intriguingly, some faint dwarfs, like those orbiting the Milky Way, show cores that appear smoother than expected, as if something has been chipping away at their dark matter hearts. Right now, experiments are closing in on the truth. Deep underground, detectors like LUX Zeppelin listen for the faint tremors of a dark matter particle bumping into ordinary matter. In space, telescopes like Euclid map the shapes of millions of halos, searching for subtle distortions that could betray self-interactions. And in labs worldwide, physicists are recreating cosmic conditions to test whether dark matter might have hidden forces of its own. Whether dark matter communicates with itself or not, the very question forces us to rethink the invisible majority of our universe. If it does interact, it's not just a passive backdrop, it's a dynamic player, shaping galaxies in ways we're only beginning to decipher. And if it doesn't, then those stubborn cosmic collisions are pointing to something even stranger, a mystery waiting to unravel in the darkness between the stars. Stretching across billions of light years like an invisible spiderweb, the cosmic web is the universe's largest structure, and dark matter halos are the threads weaving it all together. Picture the night sky as a city seen from space. Galaxies cluster like streetlights, tracing glowing roads that intersect in sprawling hubs. But those bright dots are just the endpoints. The real infrastructure lies in the darkness between them, where dark matter forms vast, intertwining filaments that funnel gas and galaxies into place. This hidden architecture dictates where stars ignite, where galaxies collide, and ultimately where life itself might emerge. The blueprint starts with the Big Bang. Tiny quantum fluctuations, random ripples in the newborn universe, got stretched to cosmic proportions as space expanded. These became the seeds for dark matter's gravitational pull, where slightly denser patches attracted more matter over billions of years. Slowly, halos formed at these knots, growing like beads on a string as filaments of dark matter linked them across the void. Simulations reveal these filaments can stretch for hundreds of millions of light years, funneling gas so efficiently they act as cosmic highways, guiding galaxies toward colossal intersections like the Laniakea supercluster, our home in the web. Yet for all their grandeur, these filaments remain ghostly. Unlike galaxies which blaze with starlight, the cosmic web's dark matter strands leave no visible trace except when they bend reality itself. Astronomers spot them indirectly through gravitational lensing, where distant galaxies appear stretched and warped as their light passes through these invisible threads. The Dark Energy Survey even mapped the web in 3 dimensions by tracking how galaxies align along its hidden currents, like leaves floating on an unseen river. The most astonishing detail: this web is dynamic. Dark matter filaments vibrate with streams of gas and galaxies in motion, while halos at their intersections grow into monstrous galaxy clusters, weighing as much as a quadrillion suns. Meanwhile, voids, the web's empty pockets, span regions so devoid of matter that they defy intuition, like bubbles in a cosmic foam. What's still unclear is how precisely dark matter's properties shape the web. Would slightly warmer dark matter with faster moving particles produce fewer fine threads? Could exotic interactions between particles create unexpected knots or gaps? The answer might lie in quasars, ancient beacons whose light absorbed by hydrogen gas reveals the web's structure in the early universe. Already, these distant snapshots show the web was surprisingly mature when the cosmos was just a fraction of its current age, hinting that dark matter's influence emerged faster than we thought. As telescopes like the James Webb and future gravitational wave observatories probe deeper, we're not just mapping the universe's skeleton, we're deciphering the rules that built it. Every filament, every halo, every void whispers clues about dark matter's nature and ultimately about the fate of everything we see. The cosmic web isn't just background scenery. It's the stage upon which all galaxies dance, and dark matter is the unseen director, choreographing the grandest performance in existence. Some of the universe's greatest secrets aren't hidden in darkness. They're hiding in plain sight, spinning right before our eyes. Take dark matter halos. For decades, we assumed they were like giant, lazy whirlpools, barely rotating as they cradled galaxies. But recent observations have shattered that assumption. Some halos are spinning faster than they should be, some even whirling at hundreds of kilometers per second. It's as if the universe handed these invisible giants an extra shot of cosmic espresso, and no one knows where it came from. This isn't just a curiosity, it's a fundamental clue about how galaxies form. Angular momentum, the same force that makes a figure skater spin faster as they pull in their arms, should have been imprinted on dark matter halos in the universe's infancy. When tiny density fluctuations in the early cosmos collapsed under gravity, they should have started rotating, dragging gas and stars along for the ride. But here's the puzzle. The halos we see today don't match the predictions. Some spin wildly, others barely move at all. It's like expecting a gentle breeze and instead walking into a tornado. One theory points to cosmic collisions. When galaxies merge, their halos don't just pass through each other like ghosts. They can transfer angular momentum in chaotic ways, like two dancers grabbing each other's arms mid-twirl. Simulations show these encounters can leave halos spinning faster, slower, or even tilted on their axes. The Milky Way's own halo might bear these scars, its rotation influenced by ancient smash-ups with galaxies like Gaia Enceladus, whose remnants still swirl through our stellar neighborhood. But mergers can't explain everything. Some isolated halos, far from any galactic traffic, still rotate unexpectedly fast. Could dark matter itself carry some intrinsic spin, like particles with a built-in twirl? Or perhaps the early universe's magnetic fields, threading through primordial gas, lent halos an extra kick as they formed. There's even a wilder idea, that dark matter isn't perfectly cold but slightly warm, with particles moving fast enough to resist gravity's pull, altering how halos gather their spin over time. The stakes are high. If halos rotate too quickly, they might fling gas outward instead of compressing it into stars, potentially stunting galaxy growth. Conversely, a well-timed spin could funnel gas into dense spiral arms, sparking star birth like a cosmic whirlpool feeding a fire. The James Webb Space Telescope is now peering into infant galaxies, hunting for clues about how their halo spins shaped their fates. Meanwhile, radio astronomers measure hydrogen clouds in distant halos, tracing rotations that defy expectations. Every new observation tightens the knot. The spin mystery isn't just about motion, it's about memory. Dark matter halos might be preserving traces of the universe's violent youth, from the first gravitational waves to the shock waves of long-dead quasars. And until we unravel why some halos whirl while others slumber, we're missing a crucial chapter in the story of how the cosmos built everything we see, and much, much more that we don't. In a universe where dark matter supposedly reigns supreme, a few cosmic rebels defy the rules. Dwarf galaxies like NGC 1052 and NGC 1052 DF2, which spin and move as if their invisible anchors have been cut loose. These galaxies, some nearly devoid of dark matter, shouldn't exist under standard theories. If dark matter halos are the gravitational glue holding galaxies together, how can entire galaxies, especially small, fragile ones, survive without it? This isn't just a minor inconsistency. It's a full-blown cosmic paradox that forces us to rethink whether our understanding of dark matter is fundamentally flawed, or if we're witnessing something even stranger. The discovery of these oddballs sent shockwaves through astrophysics. Take NGC 1052DF2, a ghostly smear of stars drifting near the Milky Way. When astronomers measured its rotation, they found its stars moved at a leisurely pace, far too slow for a galaxy of its size unless it was missing the dark matter halo that should be propping it up. Without that extra gravity, the stars should have scattered like dust in the wind. Yet here it is, intact, challenging the very foundation of modern cosmology. It's like finding a bridge standing firm with no support beams, an architectural impossibility that defies physics as we know it. Skeptics saw these outliers as a death knell for dark matter theory. If some galaxies lack halos, they argued, maybe dark matter doesn't exist at all, and our models of gravity need revising. Alternative theories like modified Newtonian dynamics gained traction, proposing that gravity behaves differently at cosmic scales, eliminating the need for invisible matter. But the plot thickened when further observations revealed that most dark matter-deficient dwarfs exist near massive galaxies, like Andromeda or the Milky Way. This proximity suggests a sinister possibility. Perhaps these dwarfs didn't start without dark matter, they had it stolen. Galactic robbery might sound like science fiction, but the evidence is compelling. When a small galaxy ventures too close to a giant like the Milky Way, tidal forces, the same gravitational tug that creates ocean tides, can rip away its dark matter halo long before its stars are affected. Picture a handful of sand tossed into a storm. The finer grains dark matter gets swept away while the larger pebble stars remain. Over time, repeated close passes could strip a dwarf galaxy clean, leaving only visible stars behind as a cosmic decoy. Yet not all dark matter-free dwarfs fit this explanation. Some, like NGC 1052DF4, float in isolation, far from any galaxy massive enough to mug them. This raises even wilder possibilities. Could dark matter be clumpier than we thought, leaving gaps where galaxies form without it? Or might these outliers be tidal dwarfs, fragments shredded from larger galaxies during collisions, born without dark matter from the start? The debate rages on, with each new discovery adding twists. The James Webb Space Telescope is now probing these enigmatic dwarfs, searching for chemical fingerprints that could reveal their origins. Meanwhile, simulations test whether alternative dark matter particles like fuzzy or interacting dark matter could produce galaxies that occasionally buck the trend. One thing's certain, these rule-breaking dwarfs aren't just curiosities, they're stress tests for our entire understanding of the cosmos. If dark matter is real, why do some galaxies escape its grasp? And if it's not, how do we explain the overwhelming evidence from galaxy clusters, gravitational lensing, and the cosmic web? The answers might not just solve a puzzle, they could rewrite the rules of the universe itself. Dark matter halos might be invisible, but they aren't all the same. Some could be icy cold, while others hum with a warmth that defies expectations. This is the temperature paradox, a debate that cuts to the heart of what dark matter actually is. For decades, the leading theory claimed dark matter must be cold, heavy, slow-moving particles that clump together easily, forming the dense cores of halos we see in simulations. But the universe keeps handing us clues that don't fit. Some halos are too smooth, some galaxies too sparse, as if dark matter's behavior isn't as simple as we assumed. Take the cold in cold dark matter. It doesn't mean chilly in the traditional sense, it refers to particles moving sluggishly, their low speeds allowing gravity to gather them into tight knots early in cosmic history. These clumps then seeded galaxies, creating the universe's large-scale structure. The theory works beautifully for massive halos anchoring galaxy clusters. But when we zoom in on dwarf galaxies, something's off. Their halos appear less concentrated than simulations predict, almost as if dark matter was stirred too vigorously, resisting gravity's pull. This is where warm, dark matter enters the scene, particles slightly lighter and faster, their extra motion preventing them from condensing as densely. The evidence for warmth comes from the smallest galaxies. If dark matter were purely cold, we'd expect countless tiny halos peppering the cosmos, each potentially hosting a minuscule galaxy. Yet observations show far fewer dwarfs than predicted. Warm dark matter's gentler clumping could explain the shortage, its particles' slight velocity smoothing out the smallest fluctuations. There's even a candidate particle, the sterile neutrino, a hypothetical heavyweight cousin to the neutrino that could carry just enough energy to warm things up without overheating the cosmic recipe. Then there's the radical fringe, hot dark matter, particles moving near light speed. These would have resisted clumping almost entirely, producing a universe where galaxies form much later and in vastly different configurations. Observations have all but ruled this out. The cosmic web's intricate filaments and galaxy clusters' early emergence contradict the idea. Yet, intriguingly, traces of hot dark matter might still linger. Neutrinos, though not the primary dark matter candidate, contribute a whisper of warmth, their ghostly flight subtly shaping how structures evolve. The paradox deepens when we look at the universe's infancy. The cosmic microwave background, a snapshot of the cosmos at 380,000 years old, shows density variations that align neatly with cold dark matter. But later, when galaxies start forming, the story gets messy. Some primordial gas clouds collapse too quickly, as if dark matter's grip was stronger than models allow. Others, like the ultra-diffuse galaxies we've discussed, seem barely anchored at all. Could dark matter's temperature vary across cosmic environments? Or might it interact with itself or other forces in ways that mimic warmth in some contexts and coldness in others? Experiments are closing in. Particle colliders hunt for hypothetical dark matter particles, while telescopes map the distribution of dwarf galaxies, probing halo structure. Even gravitational wave detectors could indirectly sense dark matter's thermal fingerprints, as the timing of collisions between neutron stars might be influenced by unseen halos along their line of sight. What's clear is this: dark matter's temperature isn't just academic nitpicking. It shapes how galaxies form, how they cluster, even how life might arise in the universe. A slightly warmer dark matter universe might lack the dense dwarf galaxies where the first stars flared to life, while an overly cold one could overcrowd the cosmos with dead-end halos, sterile and starless. The balance between cold, warm, and hot could be the fine-tuning that made our universe possible, or the clue that leads us to a deeper truth. Until we solve it, every observation, from the faintest dwarf to the largest supercluster, is a piece of this thermal puzzle, written in the invisible ink of the cosmos. If dark matter halos are as ancient and massive as we believe, where are all their smaller counterparts, the countless subhalos that should be orbiting inside them like cosmic moons? According to supercomputer simulations, a halo like the Milky Way should host thousands of these smaller clumps, each a tiny island of dark matter with enough gravity to potentially cradle a dwarf galaxy. Yet when we scan our galactic neighborhood, we find only a fraction of that number. This glaring mismatch between the subhalos we expect and the ones we actually see isn't just a minor observational hiccup. It's a crack in the foundation of our understanding of how dark matter behaves. The math is undeniable. When physicists model the birth and growth of dark matter halos, they trace tiny fluctuations in the early universe regions where dark matter was slightly denser than average. These patches collapse under gravity, merging and merging again, forming a hierarchy of structures, massive parent halos teeming with smaller subhalos, which in turn may contain even tinier fragments. It's a cosmic matryoshka doll with dark matter clumping at every scale. The simulations are precise, grounded in well-tested physics, and they predict a sky filled with far more subhalos and, by extension, dwarf galaxies than we observe. So where did they go? One possibility is that many subhalos exist but never manage to attract enough gas to light up with stars. Dark matter's gravity might have been too weak in these smaller clumps to pull in sufficient material, leaving them eternally dark, ghostly islands adrift in the Milky Way's halo. Imagine tossing handfuls of dust into a gentle breeze. Most particles drift away, never gathering into anything solid. Similarly, these failed subhalos could be everywhere, invisible to our telescopes, detectable only through their faint gravitational whispers. But there's a twist. Even counting ultra-faint dwarfs galaxies so dim they're barely more than a handful of stars, we're still missing hundreds, if not thousands, of expected structures. This has led some scientists to question whether dark matter might be slightly warmer than we've assumed. In this scenario, the particles would have moved faster in the early universe, smoothing out the smallest density fluctuations before they could collapse into subhalos. It's like trying to build sandcastles in a stiff wind. The smallest structures never get a chance to form. Yet the plot thickens when we look beyond our own galaxy. In some distant clusters, gravitational lensing has revealed hints of rogue subhalos, dark, starless clumps warping spacetime like invisible boulders in a stream. Could these be the missing pieces, or are they something else entirely, like primordial black holes or dense knots of exotic matter? The answer might lie in the faintest galaxies we've yet to discover. Telescopes like the Vera Rubin Observatory are scanning the skies for these elusive objects, while astronomers pore over data from the Gaia spacecraft, tracking the subtle wobbles of stars that could betray an unseen subhalo's pull. What's at stake here isn't just a head count of cosmic ghosts. If subhalos are truly absent, it could mean dark matter interacts with itself or other forces in ways we've never imagined, perhaps even creating friction that erodes smaller clumps over time. On the other hand, if they're just hiding in the shadows, waiting to be found, their discovery could reshape our map of the Milky Way's hidden architecture. Either way, the missing subhalos aren't just gaps in our observations, they're portals to a deeper understanding of the invisible universe. And every one we find or don't find brings us closer to unraveling dark matter's ultimate secrets. Dark matter halos have always been portrayed as vast, shapeless cocoons, amorphous clouds of invisible particles wrapping around galaxies like cosmic mist. But what if that's only half the story? A growing faction of astronomers suspects dark matter might not always be so formless. In certain galaxies, it could collapse into flattened disks or clumpy ribbons, structures far more intricate than the smooth, spherical halos we've come to expect. This isn't just a stylistic debate, it's a fundamental disagreement over how dark matter behaves, and the evidence on both sides is rewriting the rules. Start with spiral galaxies like our Milky Way. Their brilliant disks of stars and gas spin with such precision that some researchers argue an unseen dark disk must lurk within them, adding extra gravitational stability. How would such a disk form? One theory suggests that as ordinary matter, gas and stars settled into the galaxy's plane, dark matter could have been dragged along, slowed by subtle interactions we don't yet understand. Over billions of years, it might have pooled into a shadowy mirror of the visible disk, its gravity subtly tugging on nearby stars. Observations of stellar motions near the Milky Way's midplane hint at this possibility, with some stars wobbling as if guided by an invisible hand beneath them. Yet not all galaxies play along. In elliptical galaxies, blob-like collections of ancient stars, dark matter shows no preference for disks. Instead, it clumps unevenly, pooling in off-center knots that gravitational lensing reveals as distorted patches bending light from background objects. Even more puzzling, some dwarf galaxies exhibit almost no dark matter concentration at their cores, as if their halos were scooped out, leaving behind ghostly shells. These contradictions suggest dark matter's structure might depend on a galaxy's history. Violent mergers could shred nascent disks, while quiet, isolated galaxies might let them form. The debate reaches cosmic proportions when simulations enter the picture. Most models treat dark matter as collisionless, meaning particles pass through each other without a whisper, naturally forming smooth halos. But tweak the assumptions allow dark matter particles to interact even faintly, like ships brushing in a fog, and everything changes. Suddenly, halos develop substructures, filaments, lumps, even disks. Some theorists argue this could solve multiple mysteries at once, from the Milky Way's strange satellite galaxy arrangements to the odd rotations of certain dwarf galaxies. Critics, though, point to a glaring problem. If dark matter can form disks or clumps, why don't we see more evidence of them? The bullet cluster, for instance, shows dark matter behaving exactly as the smooth halo model predicts, gliding through a galactic collision unfazed. If dark matter could clump or flatten, shouldn't such violent encounters leave it distorted, like putty stretched thin? The answer might lie in a cosmic balancing act. Perhaps dark matter is neither entirely smooth nor sharply structured, but something in between, a chameleon that adapts to its environment. In dense, turbulent regions like galaxy clusters, it might stay diffuse, while in quieter spirals it could settle into disks. Or maybe we're seeing different flavors of dark matter with varied behaviors across the universe. For now, the halo disk debate remains wide open, a reminder that the universe's most abundant substance is also its most enigmatic. Every new observation, whether of wobbling stars, warped light, or ghostly galaxies, adds another piece to the puzzle. And until we solve it, we're left with a universe far more textured, far more intricate than we ever imagined. Galaxies don't drift through the cosmos peacefully. They collide, merge, and sometimes devour each other whole. And behind every cosmic smash-up, dark matter halos are the unseen puppet masters, orchestrating these violent encounters with invisible gravitational strings. Take the impending collision between the Milky Way and Andromeda, two spiral galaxies currently hurtling toward each other at 250,000 miles per hour. When they finally meet in about 4.5 billion years, the chaos won't just involve stars and gas. It'll be a showdown between their colossal dark matter halos, whose gravitational pull will determine the fate of both galaxies. Here's how it works. As Andromeda and the Milky Way draw closer, their halos will touch first, long before their visible disks overlap. Dark matter doesn't feel friction or pressure, so these halos will begin to stretch and intertwine like ghostly hands clasping in the void. Their gravity will warp the trajectories of stars, flinging some into wild new orbits while dragging others toward the merging cores. Yet despite this violence, actual stellar collisions will be rare. Galaxies are mostly empty space after all. The real action will happen in the invisible realm, where the halos merge seamlessly, their combined gravity creating a new, even more massive anchor for the resulting hybrid galaxy. This process isn't unique to our future fate. Across the universe, galaxies grow by cannibalizing smaller neighbors, and dark matter halos are the ultimate enablers. When a large galaxy like the Milky Way approaches a dwarf, the smaller galaxy's halo is the first thing stripped away, torn apart by tidal forces long before its stars are disturbed. Like a spider dismantling a caught fly, the larger halo dismantles the smaller one's structure, absorbing its dark matter while leaving behind streams of orphaned stars, telltale signs of past meals. The Sagittarius dwarf spheroidal, for example, is currently being devoured by the Milky Way, its stars smeared across our sky in a shimmering arc, while its dark matter disperses into our halo's depths. But mergers aren't just about destruction, they're also creative forces. When two massive galaxies like Andromeda and the Milky Way collide, their halos don't just combine, they trigger bursts of star formation by compressing gas clouds in their messy wake. The resulting galaxy, often an elliptical blob nicknamed Milkdromeda, will bear little resemblance to its spiral progenitors, its shape sculpted by the now merged halo's new gravitational profile. Even more intriguing, some of the merged halo's dark matter might be ejected entirely, slingshotted into intergalactic space by the chaotic dance, leaving behind a gravitational footprint that future astronomers could one day trace. The Andromeda-Milky Way merger is just one example in a long cosmic history of galactic cannibalism. From the massive, brightest cluster galaxies sitting at the hearts of galaxy clusters gorged on countless smaller galaxies, to the shredded remnants of dwarfs circling giants like the Milky Way, dark matter halos are the silent architects of this hierarchical growth. Their gravity dictates which galaxies survive, which are torn apart, and how the cosmic food chain shapes the universe we see today. And as we peer deeper into the night sky, every distorted galaxy, every stellar stream whispers the same truth. The universe is a battlefield, and dark matter is the unseen general directing the carnage from the shadows. NGC 1052DF2 isn't just another galaxy, it's a cosmic rebel, flouting the very rules that govern the universe. Discovered in 2018, this ghostly smear of stars in the constellation Cetus behaves as if the invisible hand of dark matter has let go entirely. Most galaxies rely on their dark matter halos like scaffolding, with the unseen stuff outweighing visible matter by a factor of 10 to 1. But DF2 spins lazily, its stars drifting as if there's nothing holding them together. At first glance, this shouldn't be possible. Without dark matter's gravitational grip, a galaxy this sparse should have torn itself apart billions of years ago. Yet here it is, defying expectations, forcing astronomers to ask, did we get the measurements wrong, or is the universe playing by a different set of rules? The initial observations were shocking. By tracking the motions of 10 globular clusters, dense knots of stars orbiting DF2, astronomers calculated the galaxy's mass. The result was baffling. The visible stars alone accounted for nearly all of it, leaving almost no room for dark matter. Skeptics pounced immediately. Could the measurements be off? DF2 sits nearly 65 million light-years away, making precise velocity readings of its stars notoriously tricky. If the globular clusters weren't truly bound to the galaxy, their speeds might not reflect its real mass. Others wondered if DF2 was a tidal dwarf, a shred of debris flung from a galactic collision, born without dark matter from the start. But the plot thickened with the discovery of another oddball, NGC 1052DF4, a fellow phantom seemingly devoid of dark matter. Suddenly, DF2 wasn't an isolated fluke, it was part of a pattern. Researchers scrambled to reconcile these outliers with prevailing theories. One camp doubled down on dark matter's universality, suggesting DF2's halo had been stripped away by a close encounter with a massive neighbor, leaving only the visible stars behind. Others saw a more radical opportunity. What if dark matter wasn't the only way to explain galaxy formation? Alternative theories like modified Newtonian dynamics (MND), which tweak gravity's laws rather than invoking invisible matter, gained fresh attention. The debate rages on, with each new observation adding twists. In 2021, revised measurements of DF2's distance suggested it might be slightly closer than first thought, potentially reducing the need for as much missing mass. Yet even with adjustments, the galaxy's behavior remains an enigma. Meanwhile, defenders of dark matter point to the overwhelming evidence from galaxy clusters, gravitational lensing, and the cosmic web, arguing that one or two oddballs don't outweigh centuries of consistent data. But the sheer existence of DF2 forces a humbling realization. The universe might be more inventive than our models allow. Whether it's a measurement quirk or a crack in the foundation of modern cosmology, this phantom galaxy reminds us that the cosmos still holds surprises, and the darkest ones might be the most revealing. Deep in the cosmos, mysterious explosions of radio waves flash for mere milliseconds, vanishing before we can blink, yet packing the energy of 500 million suns. Fast radio bursts, or FRBs, are among the universe's most perplexing signals, racing across billions of light-years with no clear source. But what if these cosmic enigmas aren't just random? Some scientists speculate they could be the hidden signatures of dark matter halos, invisible giants flickering in the void like ghostly lighthouses. The idea emerges from FRB's bizarre properties. These bursts are incredibly brief yet staggeringly powerful, often repeating from the same patch of sky without warning. Traditional explanations point to magnetars, hypermagnetic neutron stars, or colliding black holes. Yet some bursts defy these theories, arriving from regions seemingly empty of any obvious cosmic engines. That's where dark matter halos enter the picture. If halos contain dense knots of exotic particles, like actions or primordial black holes, their interactions could unleash bursts of energy detectable across the universe. Imagine a dark matter particle decaying after eons of stability. Its death throws releasing a torrent of radio waves, a fleeting scream in the dark. Even wilder theories suggest FRBs might be artifacts of halo structure itself. If dark matter isn't perfectly smooth but clumped into microscopic strings or domain walls, cosmic defects left over from the Big Bang, these structures could vibrate or snap under gravitational strain, sending shockwaves through space. It's like plucking an invisible violin string wrapped around a galaxy, the resulting harmonics echoing as an FRB. Some models even propose that halos act as gravitational lenses, focusing and amplifying distant bursts in ways that distort their apparent origins, sending astronomers on wild goose chases. Of course, skepticism runs deep. Critics argue that linking FRBs to dark matter is speculative at best, a cosmic Hail Mary when simpler explanations exist. But proponents counter that the universe has a habit of using the simplest solutions, not necessarily the most obvious ones. After all, dark matter halos dominate galaxies' mass. Shouldn't they leave some imprint beyond gravity? The search for answers is driving new experiments. Radio telescopes like CHIME now scan the skies around the clock, cataloging FRBs with unprecedented precision, while particle detectors hunt for action-like signals that could bridge the gap between halos and bursts. Whether or not dark matter is the culprit, the very possibility reshapes how we view halos, not just as passive gravitational wells, but as dynamic structures capable of cosmic fireworks. Every unexplained FRB is a tantalizing hint, a whisper that the universe's invisible majority might be trying to tell us something. And if even one burst traces back to a halo's hidden physics, it could crack open the dark matter puzzle at last, revealing a cosmos far stranger than we ever imagined. Right now, as you read these words, an invisible storm is raging through our solar system, a torrent of dark matter streaming past Earth at nearly 500,000 kilometers per hour. Scientists call it the dark matter hurricane, and it's not some distant cosmic phenomenon. It's happening here in our own galactic backyard. This celestial tempest isn't made of wind or rain, but of particles so elusive they pass through your body, your house, even the entire planet without leaving a trace. Yet this hurricane might be our best chance yet to finally catch dark matter in the act. The story begins with a doomed galaxy. Billions of years ago, a small dwarf galaxy named Sagittarius strayed too close to the Milky Way. Our galaxy's immense gravity shredded it apart, scattering its stars into long, shimmering ribbons that still wrap around us today. But the real legacy of this cosmic demolition isn't the stars, it's the dark matter halo that once anchored Sagittarius. When the galaxy disintegrated, its dark matter surged outward like an invisible tidal wave, and now that wave is crashing through our solar system. What makes this hurricane special isn't just its speed, it's the direction. Unlike the Milky Way's general dark matter, wind, which flows uniformly as we orbit the galaxy's center, the Sagittarius stream cuts across our path at a sharp angle. Imagine standing in a calm field while a gust suddenly whips sideways at you. For dark matter detectors on Earth, this means particles from the stream might hit us with a distinctive signature, a telltale bump in the data that stands out from the background noise. The timing couldn't be more tantalizing. Experiments like Xeno-NNT and LUX-Zeppelin, buried deep underground to shield them from cosmic interference, are more sensitive than ever. If dark matter particles interact with ordinary matter even faintly, this hurricane could be the perfect storm to reveal them. Some theories suggest the stream's particles might be slightly heavier or slower than typical dark matter, making them easier to spot. Others speculate they could interact in unexpected ways, leaving shimmering trails in supercooled liquids or vibrating crystals in lab detectors. But there's a catch. What if dark matter doesn't behave how we expect? The hurricane's particles might be too light, too fast, or too ghostly for current technology to catch. Or perhaps they interact through forces we haven't discovered yet, slipping through our experiments like sand through a sieve. Even more intriguing is the possibility that this stream isn't unique. Countless other shredded galaxies might have left similar dark matter currents crisscrossing the Milky Way, each a potential treasure trove if we learn how to look. The hurricane isn't just a scientific opportunity, it's a reminder of how dynamic our cosmic neighborhood truly is. We often picture dark matter halos as static, serene clouds. But this storm reveals their violent history, how galaxies collide, merge, and dissolve, leaving behind invisible wreckage that still shapes everything around us. Whether this stream leads to a breakthrough or not, one thing is certain: the universe's secrets aren't just hidden in distant galaxies. They're rushing past us right now, silent and unseen, waiting for the moment we finally learn how to listen. At the smallest scales of the universe, where particles flicker in and out of existence like candle flames in the wind, quantum mechanics reigns supreme, a realm of probabilities and paradoxes where certainty dissolves into waves of possibility. Could this bizarre quantum world hold the key to dark matter's stubborn elusiveness? Some physicists suspect the answer lies not in the halo's vast gravitational reach, but in their tiniest, most enigmatic building blocks, particles that defy classical physics altogether. Enter the action a hypothetical particle so light it could dance on a pinhead, yet collectively powerful enough to shape the cosmos. Actions were first dreamed up to solve an unrelated puzzle: why the strong nuclear force which glues atomic nuclei together doesn't seem to care about the direction of time. But these ghostly particles soon found a second calling as dark matter candidates. Unlike bulky WIMP, weakly interacting massive particles, actions would be feather-light, trillions of times less massive than an electron. But here's the twist: in the cold depths of dark matter halos, actions wouldn't act like individual particles at all. Quantum mechanics dictates they'd merge into a single, coherent entity, an action condensate, a wave like superfluid stretching across galaxies. Picture the halo not as a swarm of discrete particles, but as an ocean of rippling quantum energy, its waves subtly tugging on stars and bending light without ever revealing their source. This quantum haze could explain why dark matter refuses to clump as tightly as simulations predict. Action condensates would resist gravitational collapse, their wave-like nature smoothing out the dense cusps expected at halo centers. It's like trying to squeeze a cloud into a jar. The harder you press, the more it disperses. Some dwarf galaxies with their puzzlingly shallow dark matter profiles might already be showing this effect. Even stranger, actions could exhibit quantum interference, creating faint, oscillating patterns in halos, ripples in the invisible fabric of space that might one day betray their presence. But actions aren't the only quantum players in the game. Another theory posits that dark matter might be made of primordial black holes, not the stellar mass monsters we've detected merging, but asteroid-sized relics forged in the universe's first chaotic seconds. These black holes would wield quantum gravity effects near their event horizons, potentially emitting faint Hawking radiation. If such objects pepper halos, their collective glow, though unimaginably dim, might one day be spotted by ultra-sensitive infrared telescopes. The wildest idea of all, that dark matter isn't made of particles at all, but of quantum fields, invisible, omnipresent energies that permeate the cosmos like an endless symphony. In this view, halos would be regions where the field's amplitude spikes, creating localized gravitational wells without any discrete particles. It's a radical departure from traditional physics, but it could explain why dark matter seems to ignore every force except gravity. The challenge, of course, is testing these ideas. Quantum effects are notoriously fragile, collapsing under the slightest disturbance, yet experiments are rising to the task. Ultra-precise atomic clocks, chilled to near absolute zero, hunt for action-induced fluctuations in fundamental constants. Tabletop lasers scour magnetic fields for signs of actions converting into photons. Even gravitational wave detectors tuned to ever higher sensitivities might catch whispers of quantum black holes. What's at stake isn't just the identity of dark matter, it's the unification of physics itself. If quantum mechanics leaves its fingerprint on halos, it would bridge the universe's largest and smallest scales, revealing a cosmos far more interconnected than we ever dared to dream. The shadows we've chased for decades might not be hiding in the dark after all, but shimmering at the edge of perception where gravity and quantum strangeness entwine. The seeds of today's colossal dark matter halos were sown in the universe's first frenetic moments, not in the fiery glow of the Big Bang's plasma, but in the eerie quantum froth that preceded even light itself. Imagine the newborn cosmos, a trillionth of a second old, smaller than a single atom yet seething with unimaginable energy. Here, in this realm of uncertainty, tiny fluctuations, random blips in the fabric of space-time popped in and out of existence, brief wrinkles in reality governed by quantum mechanics' strange rules. Most vanished as quickly as they appeared, but a handful, stretched to cosmic proportions by the universe's explosive expansion, became the gravitational blueprints for everything we see today. These quantum ripples might seem too delicate to shape galaxies, but gravity works slowly and relentlessly. Slightly denser patches, regions where dark matter was a fraction more concentrated, began pulling in surrounding matter, growing imperceptibly heavier over millions of years. Picture a snowball rolling downhill. What starts as a tiny handful gathers mass and momentum until it's an unstoppable force. In the cosmic dark, these overdensities did the same, with dark matter's gravity acting as the invisible hand sculpting the universe's skeleton. By the time the first atoms formed, 380,000 years after the Big Bang, dark matter had already woven a vast, invisible web, its threads marking where galaxies would one day ignite. The evidence for this primordial origin story is etched into the cosmic microwave background, the afterglow of the Big Bang. Tiny temperature variations in this ancient light, some spots slightly warmer, others cooler, mirror those early density fluctuations. Warmer patches trace regions where dark matter had begun crowding, its gravity compressing and heating the primordial plasma. These imprints are more than relics, they're the universe's first fingerprints, revealing how microscopic randomness ballooned into galactic destiny. Yet mysteries linger. Why did certain fluctuations win the cosmic lottery, growing into halos while others faded? Some theories point to inflationary physics, a period of faster-than-light expansion that magnified quantum jitters into cosmic-scale structures. Others speculate that dark matter's own unique properties, like interactions with hypothetical particles called inflatons, might have tilted the scales. The wildest idea, that our universe's web of halos is just one possibility among infinite others, a single thread in a multiverse tapestry where every quantum fluctuation spawned a different cosmic story. What's certain is this: the halos we see today are time capsules preserving the universe's earliest whispers. Their shapes, their distributions, even their spin patterns might encode secrets about the Big Bang's violent birth. As telescopes peer deeper into the cosmic dawn and particle detectors hunt for dark matter's identity, we're not just studying the cosmos, we're decoding its creation myth, one invisible halo at a time. Billions of years from now, when the last stars have flickered out and galaxies fade to black, dark matter halos will still linger. silent, invisible, and indestructible. Or will they? The ultimate fate of these cosmic giants depends on a cosmic tug of war between two invisible forces: dark matter's relentless gravity and dark energy's accelerating expansion. As the universe stretches toward infinity, halos won't just vanish. They'll transform, merge, and perhaps even betray secrets about the cosmos we can't yet imagine. Consider the scale of what's at stake. Today, dark matter halos act as galactic anchors, their gravity counteracting dark energy's outward push on local scales. But as the universe expands, distances between galaxies grow exponentially, and dark energy's influence becomes unstoppable. In the short term, over the next few 100 billion years, halos will continue merging, creating ever larger gravitational wells. Galactic collisions like the impending Milky Way Andromeda smash-up will become routine, with halos blending seamlessly while their visible galaxies shred into elliptical blobs. The result: superhalos, monstrous structures weighing quadrillions of suns, each hosting thousands of orphaned stars from cannibalized galaxies. Yet even these titans won't last forever. As dark energy dominates, the universe will hit a tipping point. Halos beyond our local group, already racing away faster than light due to cosmic expansion, will vanish over the horizon, their light and gravitational influence cut off forever. Isolated halos like our own will face a slower but equally grim fate. Without fresh infalls of matter, their growth will stall. Gas needed to fuel new stars will dwindle. Existing stars will burn out or be flung into the void during chaotic mergers. The halos themselves, though indestructible in theory, might erode from within. If dark matter particles have even a minuscule chance of decaying or interacting over trillions of years, these halos could evaporate like mist in sunlight, their particles dissolving into phantom energy. But what if dark energy isn't constant? Some theories suggest it could weaken or even reverse, triggering a big crunch where the universe collapses back on itself. In this scenario, halos would flourish anew, merging into a single, universe-spanning superstructure before imploding in a gravitational maelstrom. Alternatively, if dark energy strengthens, it could tear apart halos themselves in a big rip, shredding the cosmic web at the seams. The truth might be stranger still. Halos could become cosmic fossils, the last structures standing in a cold, empty universe, their gravity too weak to pull anything together yet too stubborn to let go. The most haunting possibility: halos might outlast everything, even time itself. In a universe where protons decay and black holes evaporate, dark matter's elusive particles could be the final relic of all existence, drifting endlessly through an eternal night. Their shapes, their spin, their very presence would encode the universe's history long after all other evidence has faded. When all else is gone, halos might still whisper the story of galaxies that were, of stars that shone, and of a species that once looked up at the sky and wondered what held it all together. From the ghostly rotation of dark matter-deficient galaxies to the violent ballet of colliding halos, these 25 mysteries remind us just how much of the cosmos remains shrouded in shadow. We've traced halos colder than the void and hotter than theory allows, watched them spin too fast or not at all, and followed their invisible threads weaving galaxies together, only to find every answer births new questions. Dark matter doesn't just defy detection, it defies intuition, sculpting the universe while leaving us with paradoxes written in gravitational ink. Consider what we're up against: halos that vanish when we stare too closely, dwarf galaxies that shouldn't survive without them, and cosmic hurricanes of unseen particles rushing through our solar system. Even our best tools, supercomputers simulating billions of years in hours, telescopes capturing light from the cosmic dawn, still can't decide if dark matter is a particle, a field, or something beyond physics as we know it. The Bullet Cluster proved its existence, yet DF2 taunts us with its absence. Quantum whispers suggest wave-like halos, while missing satellites scream for warmer, wilder particles. This isn't failure, it's frontier. Each contradiction is a crack where new physics might shine through. That faint gamma ray glow around Andromeda could be dark matter decaying. Those kinked stellar streams, perhaps subhalos sculpting gravity's unseen fingerprints. Even the emptiness of cosmic void speaks volumes, their hollowness a clue to how dark matter structured the universe from its first trembling moments. So which mystery pulls at your curiosity? The phantom spin of halos that rewrite galactic formation, the rogue dwarfs dancing without dark matter's leash? Or the chilling possibility that these enigmas are just the surface, that dark matter's true nature might be stranger than every theory combined? Drop your thoughts below, and if you're hungry for more cosmic conundrums, hit subscribe. The universe has kept its secrets for 13.8 billion years, but with every telescope pointed skyward and every detector tuned to the dark, we're pulling those secrets one mind-bending halo at a time into the